IB higher level chemistry consists of 11 topics, the first of which is stoichiometry. To make sure that all topics are covered, we have the official curriculum. This is also useful for students so you can get an exact idea of what you're supposed to know. This will take a little while, but let's take a look at the official IB HL curriculum for stoichiometry. I'm going to focus on the left side here. On another slide, we can focus on the international mindedness nature, the theory of knowledge nature, and the utilization nature for this unit. And this is one of several pages. Let's have a look. Okay, first idea is that there is a particulate nature to matter and to chemical change. What we need to understand is that different elements combine in fixed ratio to form compounds. I'm thinking about balanced chemical equations, for example. Mixtures are covered. They can contain more than one element or compound that are not chemically bonded together. We need to know what a mixture is like, both homogeneous and heterogeneous. In terms of application, we'll need to deduce chemical equations and be able to balance them. Be familiar with solid, liquid, gas, and aqueous in equations. So be going through this and say, yep, I'm good on that. We need to be able to explain observable changes in physical properties during changes of state. So we should know the 6-phase changes, perhaps even more for plasma. In terms of guidance, balancing of chemical equations. Now this is what's specifically covered and not covered. Balancing of chemical equations should involve a variety of types of reactions, and we'll be covering both regular reactions as well as net ionic equations. The naming the changes of state should be covered, and we have. The mole. Here's what we should know, and here's how it should be applied. The mole is a number. It's a fixed number of particles and refers to the amount of a substance. So number one, if you know the number and it's 6.02 times 10 to the 23rd, you'll know how many particles you are dealing with. It does refer to an amount. It is one of the SI units, which is developed in France. Masses of atoms are compared on a scale relative to carbon-12, since the number of particles, or the number of atoms in exactly 12 grams of carbon-12 is how that amount was defined. And it's expressed as relative atomic mass, AMA, or AMUs. And there's also the relative formula mass, which is capital M. Molar mass, which is the most important and most commonly applied aspect of the mole, has the units of grams per mole. The empirical formula and the molecular formulas give us the simplest ratio and the actual number of atoms present in a molecule respectively, and we'll be doing, if we haven't already, lots of questions on empirical and molecular formula. How is this applied? Well, calculation of the molar masses of atoms, molecules, and formula units is something you should be able to do. You should be able to solve problems that involve the relationship between the number of particles, the amount, and the mass in grams. So gram to gram conversions, gram to molecule conversions, all of them. Interconversion of the percentage composition and the empirical formula should be something you're able to do. You should be able to determine the molecular formula of a compound given its empirical formula. This is usually a matter of scaling. And you need to know the molar mass as well to go from empirical to molecular. And we should be able to obtain and use experimental data for deriving the empirical formula from reactions involving mass changes. So if we had a experimental procedure and we got some mass changes, we should be able to figure out the empirical formula for a substance. That's what we need to know about the mole. Here's some more on the mole concept. Isn't this the same thing? Yes, that was the same topic. So let's take a look at the final topic, which is gases and solutions. Understandings. Reactants can be either limiting or excess, and so we'll do lots of problems on limiting and excess reactants. The experimental yield is something that we should know and how that varies from theoretical yield. We should know that Avogadro's law enables the mole ratio of reacting gases to be determined from the volume of gases. The idea being that atoms are so small that when they're in the gaseous form, the identity of the gas very rarely matters, and that under standard temperature and pressure, 22.4 liters of any gas is a mole. That's Avogadro's law. We should know that the molar volume of a gas is a constant at specified temperature and pressure. That's what we just covered. And the molar concentration of a solution is determined by the amount of solute and the volume of solution. So this is moles per liter, but in IB chemistry we'll always say moles per cubic decimeter, where a cubic decimeter is a liter. We should know that a standard solution is one of known concentration, absolutely, and that concentration will almost always be measured in molarity. Applying this, we should be able to solve problems relating to reacting quantities, limiting and excess reactants, theoretical experimental yield, and percentage yield. We should be able to calculate the reacting volumes of gases using Avogadro's law, which we discussed above. 22.4 liters is a mole. We should be able to solve problems of analysis of graphs that involve the relationship between pressure, temperature, and volume, which graphs are a straight line, which are a curve, and y. So we should be able to solve problems relating to the ideal gas equation, PV equals nRT. Okay. For reacting masses and volumes, obtaining and using experimental volumes to calculate the molar mass of a gas from the ideal gas equation, we should be able to get grams per mole from that. There are specific modifications to the ideal gas equation that will give you it directly. I believe, for example, m equals dRT over P might be handy. Solution of problems involving molar concentration, amount of solute, and volume of solution. We should be able to use experimental data of titration, and that's the first time I've seen that word used here. So when we're doing a titration, we should be able to calculate the concentration of a solution by comparing it to a standard solution. So we will be doing some titrations right in these early units. The values for the molar volume of an ideal gas are given in the data booklet, so that's something we should be aware of. The ideal gas equation and the value of the gas constant are also given in the sections 1 and 2 of the data booklet. So that would be PV equals nRT and the value of R, which is 0.0821 liters atmosphere mole Kelvin, and the units of concentration to include both molarity, that's grams per cubic decimeter, moles per cubic decimeter. So grams per cubic decimeter is a little different. We should be able to convert that based on the molecular weight to moles per cubic decimeter, and we should also be familiar with parts per million. Finally, we should know that the use of square brackets means something specific, and that means molar concentration. Okay, that's what we need to know for the first unit, which is stoichiometry.